Welcome everybody. This is the 11th lecture. So, today we will discuss some more closure properties of regular languages. Okay. So, the first property that we are going to see is complement of a language. So, okay. So, complement is always defined with respect to a universe. So, let us say we are looking at languages over an alphabet sigma. So, sigma star is the set of all strings. So, we define complement of L. Okay, so, this is denoted by L with a bar on top is the set of all strings in sigma star minus L. Okay, all strings that are there in sigma star, but not in L. So, the question is when we ask whether the complement operation is closed for regular languages or whether regular languages are closed under the complement operation, is that if L is regular, is L bar also regular, or is the complement of L also regular? So, the answer is yes. Okay. So, if L is regular, then L bar is also regular. Okay, so, this is the first property. So, why is this true? So, again when to give a proof of this statement, we will give a constructive proof in the sense that since L is regular, we will assume there exists a DFA for L, and using the DFA for L, we will construct an automaton for L bar. Okay. So, since L is regular, let D equals Q sigma delta Q naught F be some DFA for the language L. So, what would be a DFA for the complement of L or L bar? Okay. So, observe how a DFA works. So, if a DFA gets a string, it transits from one state to another on every symbol or on every symbol of that string, and when the string ends, the DFA is in either an accept state or not an accept state. If the DFA is in accept state, the string is accepted, otherwise the string is not accepted. So, basically if I want to construct a DFA which accepts all strings that are not in L, I would just look at the complement of the set of accepting states. So, all the states that are not an accept state, to write it formally. So, we construct a DFA D prime for L bar, where D prime is equal to, so the set of states remain the same. I mean, it is essentially the same DFA except for the accept states. The alphabet remains the same, the transition function remains the same as that of D. The start state also remains the same. The only thing that changes is the set of accept state. So, in this case it will be Q minus F instead of F. Okay. So, this is the DFA for the language L bar. So, this proves that this statement is true, that if L is regular, L complement is regular. So, now let us look at the next property, that of intersection. Okay, so formally, so A intersection B is the set of all strings X such that x is in A and x is in B. Okay. So, what we will show is if L1 and L2 are regular, then L1 intersection L2 is also regular. So, how do we prove this statement? So, to prove this statement, we will actually, so instead of constructing an automaton, we will use some of the closure properties that we have seen so far. Okay. So, what are the closure properties that we have seen so far? So, earlier we have seen union, we have seen the concatenation, and we have seen the star operation, and today we saw that under complement also regular languages are closed. So, how can I write L1 intersection L2 in terms of these operations? Okay. So, here we will use a very famous result in computer science or not only computer science, but in set theory, that is due to De Morgan. It is also known as DeMorgans law, which states that L1 intersection L2 is can also be written as L1 complement union with L2 complement whole complement. Okay. So, this is De Morgan's law or De Morgan's theorem. Okay. So, this is something that all of you must have seen at some point earlier. So, we will make use of this fact. So, what we know to begin with is that L1 and L2 are regular. So, if L1 and L2 are regular, by what we just saw, L1 complement is also regular. Okay. So, L1 complement is regular and L2 complement is regular. So, if L1 complement and L2 complement are regular, then L1 complement union L2 complement is regular, and from L1 complement union L2 complement, the whole complement is also regular. So, if I write it in steps, what we have is L1 complement and L2 complement are regular, which implies that L1 complement union L2 complement is regular, which implies that L1 complement union L2 complement whole complement is regular, which is nothing but L1 intersection L2. Hence, L1 intersection L2 is regular. Okay. So, we actually used closure properties that we have seen earlier to prove this intersection. The next one that we will see is set difference. Okay. So, if A and B are two sets, okay, A minus B is defined as the set of all strings x belonging to A such that okay, let me write it in this manner. So, the set of all strings x such that x is in A and x is not in B. Okay. So, once again, if I just expand this out, I can write A set difference B as A intersection with B complement. Okay. So, now if L1 and L2 are regular, then L1 minus L2 is also regular. So, once again the proof follows by a similar logic, that if I have L1 minus L2. So, is nothing but L1 intersection L2 complement. So, if since L2 is regular, L2 complement is regular, and since L1 and L2 complement are regular, L1 intersection L2 complement is also regular. Okay. So, this proves the set difference. So, just a small point here is that, so I have only written for L1 minus L2, but the same thing can also be said for L2 set difference L1. Okay. So, by similar idea, let me write it here, also L2 minus L1 is regular. I mean, you just replace or interchange L1 and L2 in this argument. Okay. The next property that we will see is reversal of languages. Okay. So, how do we define the reverse of a language? So, the reverse of a language is defined in terms of its strings. So, we define what is the reverse of a string, and the reverse of a language is basically the reverse of all strings in the formal language. So, the reverse of a string is nothing but looking at the string from the reverse direction. Okay. So, let me define what we mean by reversal of strings and reversal of languages. So, let W equal to A1, A2, so on till AN be a string, then reverse of W is the string AN, AN minus 1, so on till A1. Okay. This is the reversed string, and for a language L subset of sigma star, reverse of L is the set of all strings W in sigma star such that reverse of W was in L. Okay. So, I look at all strings that are there in L, I reverse them, and the language that I get as a result is reverse of L. Okay. So, once again we want to study closure properties of reverse of L. In other words, we want to ask the question that if L is regular, is reverse of L also regular? Okay. And as it turns out that, like all other properties that we have seen today, this is also true. So, if L is regular, then reverse of L is also regular. Okay. So, what is the proof for this statement? How do we prove this? So, we will prove this by giving a construction. So, like the way we showed that complement is closed under regular languages are closed under complement, we will assume that since L is regular, there is a DFA for L, and using the DFA for L, we will construct an automaton for reverse of L. Okay. So, how do we construct an automaton for reverse of L? Okay. So, let D equal to q sigma delta q naught f be a DFA for L. In other words, L equals L of D. So, what is the intuition, I mean what is the idea behind constructing an automaton for reverse of L? So, the idea is look at the set of strings that are there in the language reverse of L. So, reverse of L basically contains all those strings that we get by reversing the strings in the language L. So, we will try to construct an automaton that goes back from the accept state to the start state, or whenever I have a path in my automaton or a walk in my automaton from the start state to the accept state in the automaton D, I should have another corresponding path in the new automaton that I am trying to construct, which has a walk from the accept state to the start state. Okay. So, that is essentially the idea. So, and what kind of a automaton will it be? Will it be deterministic or non-deterministic? Okay. So, let us look at an example. So, or let us look at a pictorial representation. So, let us say this is the automaton D that we have. Okay. So, we have the start state Q0, maybe this is a accept state F1, this is another accept state F2. Okay. Okay. And maybe we have other states. So, we have a state here which has maybe 2 arrows coming to it from 0, and there is something going to another state on a 1, and so on. So, what we will do is we will reverse all the transitions that we have, or in other words we will think of this as a graph, and we will construct another directed graph where all the transitions are reversed. But now, if I reverse all the transitions, okay, what do we get? So, we will get another automaton D prime, let us say, where if I look at this state, okay, this has one incoming transition on 1, but it can have 2 outgoing transitions on a 0. Okay. So, it is not necessary that the from every state on an input symbol there is a unique transition. You can have 2 transitions, you can have more than 2 transitions, and you can also have 0 transition. So, in essence what we get is not a DFA, but we get a NFA. Okay. And the start state of the NFA will be we will non-deterministically decide which final state do I want to start from. So, instead of, so we have F1 and F2 over here. Okay. So, I will construct a new state, let us call it Q naught prime, and I will add epsilon transition to all my accept state in the DFA D, and my accept state of D prime is going to be the start state of D. Okay. So, this is essentially the idea. So, formally let us represent the DFA D prime. So, how do we formally define D prime? So, define an NFA D prime equals Q prime, sigma is going to stay the same, delta prime, Q naught prime, and F prime, okay, where Q prime is basically Q union with a new state, I will call it this Q naught prime, this new start state that I am adding, delta prime from a state Q on a symbol A. what are the states that we go to? So, from delta prime on Q on A, I will go to all states R such that delta. So, let us try to picture this. So, from delta prime on Q, from a state Q on a symbol A, I go to all those states such that from those states I had a transition on the same symbol to Q. Okay. So, all those states are such that delta R comma A had taken me to Q. Okay. And I also need to add a transition corresponding to this Q naught prime. So, delta prime of Q naught prime on epsilon should take me to all states F such that F was a accept state in the DFAD. So, we have delta prime done. Q naught prime is of course, I have defined that as an extra state. And what is F prime? So, F prime is the set which contains only the start state of the DFAD. So, this is the unique accept state of the NFAD prime. Okay. So, then L of D prime is nothing but reverse of the language L. So, we have constructed an NFA which accepts the reverse of the language L, hence reverse of L is regular. Okay. Okay. So, now we will look at two more operations and we will study closure properties under those operations. These are slightly non-conventional. So, these are related to what are known as homomorphisms of strings. Okay. So, first let us understand how, let us look at the definition of homomorphism. So, let sigma be an alphabet. Okay. So, sigma is some alphabet. So, a homomorphism H is a map from sigma to some okay, 1 second. So, let me just, we can have different alphabets. So, let sigma comma gamma be two alphabets. I mean, they can be different alphabets. One can be over 0, 1, the other can be ABC or even they can be the same. It is not necessary that they are different, maybe both are 0, 1. So, this is also the alphabet 0, 1, this is also the alphabet consisting of 0, 1. Okay. So, then a homomorphism H is a map from sigma to gamma star. Okay. So, basically what it does is that for every symbol in sigma, it gives a string in gamma. Okay. So, some string over the alphabet gamma. So, now such that, so now we can define homomorphism of strings also. So, let W be a string in sigma star, then H of W So let us write, so let W equals A1, A2 up to AN be a string in sigma star, then H of W is basically the string H A1 concatenated with H A2 concatenated with H A3, so on till H AN. Okay. So basically every string in sigma star is mapped to some string in belonging to gamma star. Okay. So the closure property that we have with homomorphism is that if okay, so before I define the closure property, let me define what is homomorphism of a language. So this gives us homomorphism of a string. So now let L be a language in sigma star. H of L is defined as set of all strings W belonging to gamma star such that so I will write it as set of all strings H of W belonging to gamma star such that W belongs to L. Okay. So I look at all strings W that are in the language L, and I look at what is the map of that string with respect to the homomorphism H. So now we are ready to state our the closure property, that if L is regular, then H of L is also regular. Okay. And the reason why this is true, I mean I am not going to give a proof of this, I am just going to briefly give a idea. So you look at, so since L is regular, there will be some regular expression for L. Okay. So look at the regular expression for L. So in the regular expression will consist of symbols from your set, your alphabet sigma. So replace every symbol in sigma with the corresponding homomorphism. Okay. So replace A belonging to sigma with H of A, that will give you a new regular expression, and that will be the regular expression for the language H of L. Okay. So that is essentially the idea. Similar to homomorphism, or we can study the inverse of it, which is known as inverse homomorphism. Okay. So let us say that H from sigma to gamma star is a homomorphism, then for a language L belonging to gamma star. Okay, so take some language in gamma star, I can define the inverse of this language with respect to H. Define H inverse of L, okay, as the set of all strings W in sigma star such that H of W belongs to the language L. Okay. So if you want to treat it as a map, so let us say this is sigma star, we have gamma star. So if I take a language L over here, look at all the strings that map to some string in L. okay, and so on. So, the collection of all the strings which map to some string belonging to L is the language H inverse of L. And what we again can prove is that if L is regular, then H inverse of L is also regular. So, I am not going to give a proof of this fact, but I will just leave it as an exercise for you to try out. Okay. Thank you.